Welcome, guys. I want to welcome Lee Dockstetter. He's going to talk to us about the justification of 3D printing and some really cool technology. So welcome, Lee.
Thanks for having us. So I'm Lee Dockstetter. I work for Hewlett-Packard. I look after production application development. I'm going to talk about justifying 3D printing for low-volume production. First, a little bit about HP. Yes, it was started at Garage in 1939 in Palo Alto by Bill and Dave. Startup capital is $538. The first product was an audio oscillator for Walt Disney Studios, and that was actually for the movie Fantasia, very first customer. I'm going to talk a little bit about 3D printing for healthcare because that industry has already transformed several applications into true production. So all rapid prototyping parts are very similar, right? It's plastic, thin walls, usually designed for injection molding. But for production applications, the needs are very, very different. For healthcare applications, there have been some fantastic developments. You may have just read about the cojoined twins that were up in Boston that got separated. All the medical models used for that, the titanium jaw for a lady in the Netherlands. Some fascinating applications and great medical advancements, but there are dozens of parts a year, maybe dozens of parts every few years. But there are several applications that have made it to mainstream. Yes, everybody's heard about some of these fantastic things. There's a children's hospital out in Arizona that's doing wonderful stuff for heart surgery. But most people don't know that there's more custom medical devices printed per day than all the industrial applications in the world combined. And it's just these four applications: orthodontics, dental prosthetics, hearing aids, and orthopedics. A little bit about that. For orthodontics, everybody's probably heard of Invisalign treatment from the company Align Technology. They are the largest 3D printing user in the world. Nobody's even close. Over 150,000 parts per day just from this one application. In other dental applications, implant surgical guides, dental models from intraoral scanners, partial frameworks for dentures, all the wax-ups for crown and bridge, impression trays, tens of thousands of parts every day are being 3D printed. Hearing aids, why did that transformed probably 10 or 12 years ago? 5 companies in the world make up 80–90% of all the hearing aids. Today there's 2 ways to capture the inside of your ear. One is with silicon molding, and then you scan the mold. There's a new technology coming out in the ear scanner. It's about 30 seconds to 60 seconds per ear, captures a really, really good impression of the inside of your ear. You do a CAD design for that. You go out to a 3D printer with biocompatible material. That becomes the shell. So why did this industry change over so quickly? Well, it turns out when the hearing aid doctor prescribes a device, if it doesn't fit, it's a free remake for the vendor. And the return rate was like 20%. With digital impressions and digital remakes, it dropped to under 10%. So the entire industry changed in maybe a period of 3 or 4 years. Tens of thousands are made every day. Over 60 million have already been 3D printed. Orthopedics, about 650,000 total knee replacements are done per year. About 10% of those are using custom 3D printed surgical guides. So you take a size medium knee and you make a customized surgical guide to cut to fit to the medium size. And a biomedical engineer designs all that up front, saves 30–40 minutes of surgery time per patient. At $10,000 an hour for a surgical theater, the savings are quite a lot. So why did those applications make the transformation from traditional manufacturing into the 3D printing? it was because the data was there, the ecosystem was there. The Dental and the hearing aid software is completely specialized for those applications. You're not taking general purpose CAD systems and trying to do ear canal models. There's very special software that 3 to 5 minutes per shell, you can design and produce a customized hearing aid. And it's not just the design. It's an end-to-end solution. So there's a scanner, there's a database, there's manufacturing software, there's tracking, there's part ID, interfacing to the ERP system. It's not just the 3D printing, it's the entire end-to-end solution is why those applications have made it over the chasm. So why do people move to 3D for production? Several ways to justify it. It's an economic advantage, or it's faster, or it's a better product, or it's something completely new like the Invisalign. I'll go over some of those examples. So economic justification, if it's a one-off, high value, like a baby helmet for reshaping a deformed skull, it's a one-off, quite a high value application. Or purely economic. If you've got 500 parts to build and it's a $20,000 tool, is it cheaper to print it or is it cheaper to tool up? Okay, that's a pretty easy one. And that's what we show here on this graph. Digital, the cost per part is going to be about the same regardless of the volumes that you're printing, whereas the traditional tooling cost is amortized over the number of parts. So where those cross over, we call that the return on investment or the crossover point for justification for 3D printing. And those are kind of the hard numbers. The soft numbers are if you make extras because you don't want to have to pay for the setup cost for a tool. If you buy 10,000 extra parts and they're never used, they have to be scrapped. There's a lot of soft numbers that go along with that as well, plus the inventory cost of maintaining those, maintaining the tool, all that kind of stuff goes into the soft cost comparing digital versus traditional manufacturing. So we looked at our own devices. We had some low volume but high value products. Not too many people know HP makes $5 to $8 million digital 3D printer, 2D printers. Big, huge, 1,000 feet per minute devices. They sell hundreds of those a year. Some bigger poster, billboard type printers, thousands of those per year. So we took a look at those versus our medium and our high value high quantity, and we looked at what should be 3D printed. So in our technology, I'll give you a really simple example of how it costing is. It's about $70 a vertical inch. And so on the first product that we have, the HP Jet Fusion 4200, the build area is 12 inches by 16 inches by 16 inches. So the refresh rate on that is 20%. So if you do the numbers, it comes out to $70 a vertical inch. So if you look at the example on the screen here, the custom braces, you can get 5 parts about 5 inch tall, so it's going to be $350 to make that build. So that means each part's going to be $70. If you put more parts in that, you just divide by a higher number. So quick way to do a justification on printed parts versus molded parts. So we looked at our own products, and this is the Jet Fusion 4200 and its post-processing station. And with the pricing of where we're at today for the machine, the post-processing, the consumables, the maintenance contract, the depreciation of the machine, about half of the 3D printed parts, or half of the plastic parts in these machines will be 3D printed, right? You gotta like it. 3D printers printing itself. Where we're going with the open material strategy, faster machines, lower cost machines, next generation type machines, another 50% of those parts will be able to be 3D printed. And that's where we're going. Another one is a part redesign, right? This isn't replacing a plastic part with another plastic part. This is actually a carriage head part from one of our large format printers. It was about a $22 part machined out of aluminum. Some engineers redesigned it to be 3D printed. It's about a quarter of the price, and it's about a fifth or a seventh of the weight, right? So better performance, lower cost, and print on demand. This is kind of a part recombination. This is, again, another part from inside one of our machines. It's a manifold. So there were several parts, screws, wires, gaskets, for those things to go together. And it was pretty expensive, $194 depending on how many were printed off the molds. You combine all of those, and it's less than $100. And I would give the guy who designed this maybe a B as far as his first effort. He just combined the existing parts that were designed for injection molding. This is the manifold for powder and air handling. So if you're going to actually design it for 3D printing, you'd have smooth walls for better airflow. You wouldn't have to worry about draft angle or parting lines. You could design it all as one piece. And there's several more examples. This made it out to some other products. Look at this vacuum manifold here. For the tooling cost was $84,000, and the injection molding cost was only a few dollars, but on the volume of parts that were going to be printed or molded, the 3D printed part turns out to be about half the cost of the injection molded. So tooling and jigs and fixtures go across all parts, all applications, and there's a huge advantage in tooling up jigs and fixtures. And now with the HP technology, actually part production is going to be about half the cost of other competing technologies. But making that jump into designing parts for 3D printing is a huge jump for companies. I mean, even within Hewlett-Packard, we don't do our own molding. We outsource the molding to somebody. So are traditional molding companies going to do that? Are we going to print these ourselves? What about tolerances? You know, everybody's used to plastic injection molded tolerances. 3D printing is not quite where injection molding is today, but it's getting there. But understanding how all that's going to work with your vendors, the guy who's designing it, the guy who's sourcing it, that all has to be dealt with. You know, but it's going to open up shorter runs, personalization, demand flexibility, spare parts down the road. What if somebody came up with a better way to design a part or have a part perform better in a machine, but it's already been tooled? Are you going to go retool for the change the part? Yeah, probably not. You might wait for the next version of the machine. With 3D printing, you can actually change parts on the fly. So what needs to change in R&D? Parts need to be designed differently. Look at this example of a metal part. You know, that's kind of welded together. Look at the first generation redesign and then the third generation redesign. So you need to design for additive manufacturing, and that takes a while for retrain your folks, allow them to fail, all those kind of sort of things. And then even the design tools, there are some tools coming on, some plugins that will actually help the engineer specify maybe the performance and then let the machine do the hollowing and the webbing. And then what about tracking it? What if every part is going to be personalized? How does your product life management system, how does your ERP system handle that? How do you do product ID? How do you do serialization, you know, if every part is different? It's tough. And then even in sourcing, there's design guides, there's going to be technology selection, recommendations, how thin can your walls be, how big can your letters be, what's your aspect ratio on tall parts, things like that have to be taken into consideration. And then the vendors have to be able to deal with this as well. So it's, and then how do you inspect these free-form shaped parts. So the adoption steps, you need executive support. You need the top management assign an overall champion. You agree on the pace. Maybe you start with an easy win to start with. Align the resources and promote this everywhere. So once you do have some wins, make that guy a hero, and everybody else will go, hey, I want to be a hero too. And all of a sudden, you've got a transformation in your R&D department. I'm going to go over a little bit about the HP multi-jet fusion technology, and the first product is the Jet Fusion 4200. And I'm going to point out, remember I said that we had these $5 or $7 million printers? They go up to 110 inches wide at 1,000 feet a minute on printing, and every page can be different. And they're using these ganged print heads. So you can gang these together up to 110 inches wide. We're using 3 of these. They're 4 inches wide each, so it gives us a 12-inch wide build area. I'll explain the process, and then we'll show how it works in a video here. So we roll out a powdered plastic. The first generation plastics we're going to use is the nylon 11 and nylon 12. And then we apply a fusing agent, and we apply a detailing agent. So everywhere the fusing agent is applied, we apply energy, and it melts. Right? It's not making things stick together. It's not actually adding a plastic to the part. It's only energy absorber. So when the heat bar goes over, it melts everywhere there's the fusing agent. And to keep the thermal bleed, we apply a detailing agent. And I like to show this. This was actually printed as one piece. It's scissors that will actually cut paper. The edges on here are sharp enough and detailed enough from that detailing agent.
Introducing the HP Jet Fusion 3D printing solution, made up of a printer, build unit, and processing station with fast cooling. Now you can deliver functional parts up to 10 times faster at the lowest cost. HP software enables easy job preparation and accurate job monitoring. The HP Jet Fusion 3D processing station with fast cooling is designed for a cleaner, more efficient 3D printing workflow. Replacing materials is easy. With the materials loaded, the HP Jet Fusion 3D build unit slots into the printer so that production can start. Pre-print and in-printer checks enable predictable, quality output. HP Multi-Jet Fusion technology delivers extreme dimensional accuracy and optimal mechanical properties faster. Once the print job is complete, the build unit can be moved on for post-processing, and the next unit slotted into the printer so you don't have to stop production. The HP Jet Fusion 3D processing station makes post-processing easy, from faster parts cooling to cleaner unpacking and materials reuse and mixing. Keeping the powder contained so that you don't need an additional room for parts removal. New HP 3D High Reusability PA12 leads the industry in reusability, so there's less waste and less cost. And the HP Multi-Jet Fusion Open Platform gives you access to a wider range of future materials and applications. HP Jet Fusion 3D printing. Start producing more functional parts within the same day, up to 10 times faster and at the lowest cost. HP, keep reinventing.
All right, I hope you guys were able to watch that. Like I said, go to YouTube and look at HP 3D printing and you see a bit more details and some other things. What they didn't really point out in that video is each layer is 6 to 12 seconds. I just use 10 seconds because it's easier on the math. But it's 10 seconds a layer regardless of what's on the layer. So if you've got 40 sets of sunglasses on there, it's still 10 seconds a layer. If you've got one part, it's still 10 seconds a layer. But it adds up to about 2 inches per hour build speed. Okay, so depending on what you're comparing against, if you're comparing against FDM, it's 20 to 50 times faster. If you're comparing to SLS, it's on average maybe 10 times faster, depending on what's being built. It's about half the cost. So of a comparable size SLS machine from other vendors, the machine and system price is about half. The refresh rate is twice as good, and the material price is about half the list price of competing powders. So if you add all that up, the cost per part is a fraction of what is available on the market today. And it's not just the 3D printer. It's also the build unit and the post-processing. So the way this works is you take the build unit, which has the powder supply in the bottom of it that's been loaded in it by the post-processing station. You stick that in the 3D printer. It knows what material's in there. You feed the job to it. It completes. You pull the build unit out. You roll it over to the post-processing station. You stick it in. You take a second build unit, stick it back in the printer, and away you go. And that's the printing and the post-processing. So when you put it in the post-processing station with fast cooling, it will actually hold it at the proper temperature so the warpage and material properties are correct, and then it will speed up the cool down when it's appropriate. Saves about half the time of just setting it aside and letting it cool down naturally. It takes the powder out of the build unit. You pull the parts out, you dust them off. It takes all that powder, it puts it in a recycle bin, and then on the next build, it combines the right ratio of new powder plus the recycled powder and puts it back in the bottom of the build unit. So it's a really nice combination of the post-processing and getting ready for the next build. And if you wanted 2 different materials, you could have 2 different post-processing stations, and you just wipe a few things off in the machine, and the machine's going to know what materials in the build unit, and so you can run a couple of different materials on one printer. And it's not just the machine, the post-processing, it's the whole system. So we've got software and plugins that will feed the machine, and we've got printer utilities like a print spooler that will look at your fleet of machines. And we've also buddied up with a couple of software vendors, Autodesk and Materialize, so you can actually drive the machines from their software. Now, a lot of people look at me funny when I say we have an open material platform. It says, hey, you are the guys that had the razor and razor blade business for 2D printing. What the heck are you doing with 3D printing and open platform material strategy? Well, it's kind of an interesting story. HP, of course, is a large consumer of plastics, and we grill our suppliers over special formulations for a lot of high-performance parts, and it takes several weeks to go through those formulations. Well, if people are going to use this for production, they're going to do the same thing to HP, and they're going to want their own formulations. And we're not a plastic powder material formulation company, so we buddied up with the folks that are. So we'll have our own branded powder, which will be the typical prototyping type powders. But if you get into these high volume production applications, they're going to have very special requirements for their powders for both speed, mechanical properties, surface finish, those kind of things. And we're encouraging customers to buddy up with material suppliers and get their own HP certified powders. Now, does that mean any powder and any fusing agents? No, it doesn't. We have to make sure that it performs and that it's safe. But other than that, people can deal with their material suppliers directly. And we're starting with these 4, Evonik, BASF, Arkema, and Lehman & Voss. They're by far the largest high-performance plastic providers globally. And if you pick one of those for a special requirement, we're happy to work with you. So first generation machine, we're going to have the high reusability PA12 and the PA11. And then shortly after that, we're going to have an elastomer, a flame retardant, and glass-filled PA12s. After that, it's really it's going to be customer driven. What high performance polymers are you looking for? High temperature? Are you looking for additional thermoplastics, biocompatibility, those kind of things? Work with us, work with our vendors, and we'll generate the next generation together. A little bit look into the future here. We're working on color. We showed this at the Rapid Technology show in May. We're working on built-in sensors into parts. We're working on multiple agents. We showed a strain gauge built into a part and hooked up to a voltmeter to show the weight hanging. Right, so we're working on all sorts of future generation technology, and we'd love to listen to what your requirements are. So again, go to www.hp.com, go 3D printing, or contact your local reseller like our friends at TPM. So I think we are done with a standard presentation, are about ready for some questions.
Yeah, Lee, so thank you very much for all that information. We do have one question. Do you have any benchmark data regarding your parts compared to standard aluminum and other parts?
Probably not aluminum, but if you look at other plastic injection molded parts, yes, we do. Again, go to the web page, pull up the data sheet, and the mechanical properties are stated on the data sheet. It's roughly about 80% of the injection molded characteristics in the Z, and pretty close to the characteristics in the X and Y.